Our objective for this section is to be able to write the equation of motion as simple harmonic motion. This is broken up into two parts. There's what's called the simple harmonic motion, or the undamped motion equation. And then the second part would be the damped motion, where the undamped, meaning that if you have a spring or if you have some mass that is in motion, it is not being inhibited by any exterior force. But that exterior force can be something as simple as air. Air resistance can be a retard. But if you isolate air and say that any resistance is at a minimum, we talk about here simple harmonic motion, that objects are said to hover or to oscillate in nature without being what you may think retarded by some kind of external force. Well, we know that the main force that will be exerted upon any object, if there's nothing else that's going on, is typically in the Earth's atmosphere, gravity. So we are definitely calculate gravity, the acceleration due to gravity, within the calculations here. We simply, to look at what's called simple harmonic motion, or even if it's undamped motion, is to consider two historic laws, one Hooke's law and the other Newton's second law of motion. We're going to take both of those together, combine them together, and form an equation. The equation that you form is indeed the simple harmonic motion. Also, we want to be able to apply the idea of the frequency, the weight, and period of a system to determine the equation of motion. So I got a little bit bookish, and so this information right here is basically right from the book. In terms of Hooke's law, I think the main thing that you want to gather from that is that Hooke's law talks about a force. The force on a spring is said to be directly proportional to the distance of the stretch, and here S is denoted as the distance of the stretch. K is some constant of proportionality that must be determined, so we'll deal with that. If you take Hooke's law that talks about force, and if that's a force that's being exhibited from a spring, and here we have an example of a spring that is a mass hooked to a spring. You can see where it's unstretched, it's said to be at rest. And then when that mass that's on the spring is pulled, then it causes some kind of vibration effect. We call that motion harmonic motion. That harmonic motion is identical to the harmonic motion that you dealt with the power series. If you recall, there you had some summation of some term divided by some other term times n, as n goes from 1 to infinity. And you looked at what was called the harmonic series, summation of 1 over n, if you will, the simplest one. That series is trying to calculate the distance of those vibrations. And so as you go further in time, the distance gets smaller and smaller, right? And so that's what the power series was trying to get at when you looked at that back in chapter 9. I think it was section 2 or section 3 of calculus. Now, if you take Hooke's law and couple it with Newton's second law, what Newton's second law says that the force of any particular mass is said to be associated with the mass times the acceleration due to gravity. If we take those two together, so for this part here, this is Newton's law. The acceleration is that second derivative of the displacement with respect to time. And this part here is Hooke's law. The negative is set to be included because of the so-called restoring force, that you're trying to restore the system back to its equilibrium state. Now, if you have a spring like this that is a mass hooked onto a spring, so if that mass is being pulled down, then we say that this direction downward is positive direction. Right? Items or objects in space that falls down, well, it's saying to be falling the right way because that's where gravity is trying to pull it. Right? Gravity is saying, come to me, come to me. And then anything that's opposite of that is said to be of negative displacement. So if it goes back up, negative, comes back down, well, gravity is trying to pull it down, so that's like in a positive direction. And it goes in the opposite direction, and so you have a so-called negative displacement. We can form the equation from that, and if you go back to the bottom here, they're forming the equation from this part and from this guy right here. Let me see if I can write that for you in here. That we have m times, I'm just going to say this x double prime to represent that second derivative. That's equal to negative k times x. If you add kx to both sides, then you get m times x double prime plus kx is equal to 0. Dividing through here by the m, so we get x double prime plus k over m. K is the constant of proportionality, m is the mass, times x is equal to 0. This is x double prime. So what we do here is, instead of writing k over m, because you know back in grade school nobody liked fractions, so we just give it a very neat term. We call it omega squared. Omega, why? I don't know. I had a joke, but you might not get it. So omega squared is equal to m. I do know why it's being squared. Is because once I plug omega squared back in for k over m, I write the auxiliary equation, and I get something that looks smooth. So here we have x double prime plus omega squared, which is the constant, times x is equal to 0. Now the so-called auxiliary equation is of this form. This m that I'm going to write has nothing to do with the mass. It just has to do with the old auxiliary equation that we dealt with back in chapter 4. So this is m squared plus omega squared is equal to 0. I get m squared is equal to negative omega squared. M is equal to, take the square root of both sides, plus or minus, this is omega I. So that means that x of t is equal to, this is imaginary, so this is c sub 1 times cosine omega t plus, I need more space, x of t is equal to c sub 1 times cosine omega t plus c sub 2 sine omega t. Have you seen that equation before? This equation is the simple harmonic motion equation. That's the equation that we want to be able to produce from a particular problem. And he has all of that right here in his notes. See how he replaces the omega square to represent the k over m. And so it's that second derivative. I just said that was x double prime, just for simple notation. Right? When you solve that using your differential equations, you get x of t is equal to c sub 1 times cosine omega t plus c sub 2 times sine omega t. Yes, sir. You got it? Okay, okay. Well, just give me 1 second. I want to at least try to work a couple problems here. They're very, very simple problems. Then we'll pull that up. If you got time, we could look at that. Is that the one with the with Ajani? Okay, good. Okay, good deal. That's good. Well, hey, you got it, man. Okay, let's hurry up and do this, okay? Okay. Two things. Talk about the period. The period is given as 2 pi over omega, and so that's defined as the time that it takes for the mass to execute one cycle. And then the frequency is the reciprocal of that, so 1 over t, or omega divided by 2 pi. And that's the number of cycles completed in each second. Another formula that you need is this, and that is the weight. He doesn't give it here. The weight is also given as the mass times acceleration due to gravity. And so little g, if it's in the English system, is 32 feet per second squared. Or if it's in metric, 9.8 meters per second squared. Now, yeah. Look here. This is number 3 from the textbook. Write the equation of motion given the initial conditions. So I'm going to write the auxiliary equation, which is m squared plus 25 equal to 0. Well, that implies that m is equal to plus or minus 5i. So x of t is c sub 1 times cosine 5t plus c sub 2 times sine of 5t. Now, I used the initial conditions to find c sub 1 and c sub 2. So it says that x of 0, let's see what that's going to be. That's going to be c sub 1, cosine of 0 is 1, plus c sub 2 times sine of 0 is 0. That's equal to negative 2. So c sub 1 is equal to negative 2. Then it has x double prime. What the initial condition for x of 0, that's the initial position. And then if it's x double prime, that talks about the initial velocity, right? So here, x double prime, take the derivative first. So that gives us negative 5 c sub 1 times 5 times sine of 5t plus 5 c sub 2 times cosine 5t. Now we let t equal to 0 and set that equation equal to 10. So x prime of 0 is equal to negative 5 c sub 1. Sine of 0 is just 0 plus 5 c sub 2. Cosine of 0 is 1. And this is equal to 10. So you get 5 c sub 2 is equal to 10. We get c sub 2 is equal to 2. Right. This implies that c sub 2 is equal to 2. Well, you can write the equation of motion now, that x of t is equal to c sub 1, that's negative 2, times cosine 5t, plus c sub 2, that's 2 times, that c sub 2 is 2, times sine of 5t. Okay. That's pretty straightforward, right? Now, quickly, just give me 1 minute. There's one problem that I definitely want you to be able to see. And look, this is number 9. And then this number 11, homework problems. And then numbers 12, 13, and 16, homework problems. Very straightforward. The period, since the period is set to be t, right? The period here of this mass on a spring is pi divided by 4 seconds. Well, the formula for the period is 2 pi over omega. So I think from there, let's stop and let's find out what omega is. So this is omega times pi is equal to 8 pi. So that implies that omega is equal to 8, right? So now let's look at the next sentence. If the spring constant, that's K, right, is equal to 16 pounds per feet, it says, what is the numeric value of the weight? Find capital W. That's given to be the mass times G. So that's going to be the mass times 32. Since we're dealing with the with feet and pounds, so that's the English system. So times the mass. I need to find the mass. No problem. I know that here omega squared is given to be K over the mass. Right? And I got omega. Omega is 8. I have the spring constant at 16. I can find the mass. So we say i.e. this is 8 squared. That's equal to 6. Well, yeah, 16. Okay. K is 16, right? That's over M. So that implies that M is equal to 16 over 64. So what is that? All right. So now if omega is equal, if the mass is equal to that, I'm looking for the weight. That's the mass. This is in pounds. So this is 1 over 4 times 32. And so you get 8 pounds for the weight. And look, they all, I guarantee you, they're as simple as that. Okay. Now, can you help me pull that up, Jeremy?